Okay, these are the solutions to the derivatives practice test. Here I have number one. In the first 8 questions, I didn't say this, but you all figured it out. You're to take the derivative of the function. All right, so at number one, I have a quotient. The numerator of my quotient is e to the cosine of x, and the denominator is x squared plus the log base 3 of the tangent of x. The derivative of e to the cosine of x. This is a chain rule with an inside of cosine of x. The derivative of e to something is e to that same thing. But then I need to multiply by the derivative of that, and the derivative of cosine is negative sine of x. Then for g, I'm going to do the derivative of g. The derivative of x squared is 2x plus, now I have a logarithm. This logarithm is log base 3. So the derivative of a log base 3 is 1 over the natural log of 3 times whatever I took the logarithm of. That is tangent of x. And now I'm going to multiply by the derivative of the inside of the logarithm. The derivative of the tangent of x is secant squared of x. And notice there is an inside of tangent as well. The inside of tangent is x. So the derivative of secant squared, or the derivative, which is secant squared, will also be of x. And then I'll multiply by the derivative of x, which is 1. Okay, but I usually don't mention that. Now let's use our quotient rule. So y prime will be f prime g minus fg prime divided by g squared, and I'm simply going to fill in there. So I get e to the cosine of x. I'm going to put the negative in the front. Negative e to the cosine of x, sine of x, and I'm going to have to put this one in parentheses, x squared plus the log base 3 of the tan of x, and that is f prime g minus fg prime. F is e to the cosine of x, and g prime is 2x plus the secant squared of x over the tangent of x times the natural log of 3. I just put that natural log of 3 in the back, and I multiplied the tops and the bottoms, all divided by g squared. So that would be x squared plus the log base 3 of the tangent of x. And the only simplification that will be nice here would be to factor out an e to the cosine of x or a negative e to the cosine of x, but I'm going to leave it that way. Here's number 2. In number 2, I have a product. Notice that I have a times here, and if I look in the front, that has an x, and in the back, well, that has an x also. That's when I use the product rule, when I have two things multiplied together, both of whom are functions of x. So the first one is x squared, and that has the derivative of 2x. The second is 2 to the x, and that has a derivative of 2 to the x times the natural log of 2. This question is designed to point out the difference in these derivative rules. When your x is your base and your exponent is a number, then you use the power rule where you subtract 1. When your x is in the exponent, then you have an exponential function and your base is a constant. And so that follows the rule where exponential functions have derivatives that are equal to themselves with the addition of the natural log of the base multiplied in there. Okay, so y prime, following my product rule, would be to take the derivative of 1 at a time here. So f prime g is 2x times 2 to the x, and then fg prime would be x squared times 2 to the x times the natural log of 2. The only simplification really here would be, well, you could factor out an x and a 2 to the x, and that would leave you with 2 plus x squared ln 2 left in the left inside. All right, on number 3, it might be helpful to rethink of this as the cosecant of 2x squared plus 1 cubed. That's what we write when we mean, these both mean the same thing, We tend to just put that 3 after the C because it's less writing, but this is what's happening. This way we see the layers of the onion a little better. The outsidemost function is a cube. And so when I do this first derivative, I have to do the derivative of a cube first. Now the inside, what was cubed, is a cosecant of something. Okay, so that cosecant thing, he is not going to change. It's still whatever the cosecant was. We don't change the inside on the inside when we do a derivative, but we do multiply by the derivative at the end. So what's the derivative of a cosecant? Well, it's negative cosecant cotangent. And again, this argument, the 2x squared plus, wait, hold on, that's 2x to the 5th plus 1. This 2x to the 5th plus 1, he is never going to change. He's going to be the argument for the inside of every trig function in the derivative. So it's still going to be cosecant of negative cosecant of 2x to the 5th plus 1 times cotangent of 2x to the 5th plus 1. That was still the inside there. And now, what were we taking the cosecant of? Well, we were taking the cosecant of 2x to the 5th plus 1. That's the insidemost layer of the onion. I need to multiply by that derivative. That would be 10x to the 4th. And so this is what I mean when I'm talking about layers, peeling the onion, and that's how you do the derivative with the chain rule. The outside layer is that red cube. So I do the 3 squared. That's how you do the derivative of something cubed. It's 3 times its squared. Then inside that layer, there was a cosecant. I know the derivative of cosecant. That's negative cosecant cotangent. That gets multiplied at the end of the line. You don't reinsert it inside the inside. That's not how that works. It always gets multiplied at the end, and we leave the inside what it was. And then finally, on the innermost layer in the green, we compound and multiply by the derivative of it. Okay, this was an onion with 3 layers. The outside was cubed, the middle was cosecant, and the inside was that polynomial. Okay, next. I'm going to rewrite this one with a negative exponent so that I don't have to use the quotient rule. Okay, now when I take this derivative, I'm going to use the power rule. So my outsidemost layer is a negative 3 power. That's negative 3, and then I subtract 1 to the negative 4. And my inside is a 2x minus pi. This question is to remind you that the derivative of pi is 0 because it's a constant. Even if I had a pi squared in here, the derivative of pi squared is still 0. Okay, so be careful if you have constants that get letters and then it looks like we're operating on them. Well, they're still constants. Okay, and so that's your derivative there. I multiplied by 2 because that was the derivative of the inside function. And if we want to clean this up a little bit, this is negative 6 over 2x minus pi to the 4th. Number 5, I have a product on number 5. My first product is radical 3x. I'm going to make that 3x inside a parentheses with a 1/2 power. And then the second term is sine. Okay, and so what is the derivative of f? Well, I'm going to use the power rule here. 1/2 to the negative 1/2. Don't change that inside, but multiply by its derivative at the end. That's the chain rule there. And the derivative of x is 1. And the derivative of sine is cosine. And now for the derivative of y, I use the product rule. F prime g plus fg prime. This is going to be 3 over 2 radical 3x plus 1. That is the f prime times sine of x plus fg prime. So radical 3x plus x cosine x. That's your derivative there. I'm going to leave it there. Number 6, I have another product here. Secant of x and tangent of 2x. What is the derivative of secant? That would be secant tangent. And what is the derivative of tangent? That would be secant squared. This time the tangent was of 2x, so the secant squared will be of 2x, and then multiply by the derivative of the 2x too. So we use, by the way, some people have been asking, when do I use the chain rule? The answer is actually all the time. Every single time you take the derivative, you do have an inside, and you are taking the derivative of it at the end and multiplying by that. In this case, you kind of see what's happening is, well, what was I doing the secant of? So my outside here is secant. And the derivative of secant is secant tangent. And then the inside of that secant was x. So I leave that x in there, and then I multiply by the derivative of x at the end. That's 1. So when you multiply by the derivative at the end, when your inside is just an x, then that derivative is just 1. And so we don't always point out that we're doing the chain rule with that. In fact, we introduced this as just the formula. However, when you had tangent of 2x, its derivative is not 1. And so there you see the tangent or the chain rule better. Okay, and I'm still doing the product rule. F prime g, all right, so that's secant x, tangent x, tangent 2x. By the way, these do not combine any way. When your arguments of your trig functions, that's the inside part, the argument, are not the same, then you don't want to mess with those at all. They're not the same. Plus fg prime. So I'm going to put the 2 in the front. Secant x, secant squared of 2x. All right, there we go. Number 7, I know a lot of people are waiting for number 7. Okay, so this is just a chain rule. We have to peel back the layers of the onions, and you know that square roots are 1/2 powers. So we start by rewriting this. I'm going to take out every square root, and I'm going to make it a 1/2 power. This last one, I'm not going to use parentheses. All right, so let me color code this. This square root here in red is this parentheses to the 1/2. Then this square root right here in blue is this parentheses 1/2. But the whole red has this inside of 1 plus that square root. And then finally, the inside of the blue square root was 1 plus the square root of x, and that's here in green. Okay, so I do have 3 layers to this onion. I'm going to start by peeling off the outer layer. What is the derivative of the outer layer? Well, that's a 1/2 power, so it's simply 1/2 to the negative 1/2. What goes on the inside? Exactly what was there. Okay? I'm not changing that. That is this. These are the same things. This is 1 plus the square root of 1 plus the square root of x. All right, you can leave it with the parentheses and the 1/2 if you want. All I did was the derivative of the red. Now, multiply that by the derivative of what was blue. The blue is what was inside the parentheses of the 1/2. So it's 1 plus, well, that would be 0 plus, because the derivative of 1 is 0. Now I have this parentheses with the blue 1/2. So that's 1/2 to the negative 1/2. And don't change that inside. This green 1 plus x to the 1/2 is going to stay there. And finally, now look what was inside the blue. That was the green function. What's the derivative of the green function? 1/2 x to the negative 1/2. All right, so let me rewrite all of this in black, which is, you know how pencil works. I'm going to go ahead and go back to my 1/2 because I think that you probably were confused with the radical part. And it's fine to keep them as 1/2. This is not going to simplify nicely, and I don't even want you to try. It's an exercise in making sure you can do the chain rule. And so I got rid of the 0 plus there, and I don't need that extra outer blue parentheses. And there's your green. And so Well, I guess I can multiply 3 1/2s together. That's 1/8. Yeah. Then I wouldn't, everybody else has a negative 1/2 exponent. You don't combine them or anything, but they would just go to the denominator with a positive 1/2 exponent. But I'm not going to do that either. I'm just going to rewrite with these negative 1/2 powers. Now, technically, this answer is just one line. It's just this first line. Okay, that's the answer. You can leave it just like that. I didn't want the colors all in the answer. I wanted you to see it in black and white. And then a lot of people were worried about simplifying with good reason. And so the 1/2 multiplied to 1/8. All right, next question, number 8. Please use the log property on these. I mean, you don't have to, but it just makes life so much easier. And then don't use log properties where you're not supposed to. So this is all you can do. I guess this is all you should do at this point. Now do the derivative. That's 1 over the inside times the natural log of 3, since this is a base that was an e. Now the inside has a derivative of 2 because the logarithm was of 2x, and the derivative of 2x is 2. And then on this one, 1 over x plus 2, natural log of 3, and then the derivative of the inside there is 1. And I'm going to go ahead and cancel those 2's. 1 over x ln 3 minus 1 over x plus 2 ln 3. I don't use parentheses when they're not necessary. This x plus 2, it has to be in parentheses. All right, so that's our answer there. On 9, it says to find the equation of a tangent line. That was a poor point that I gave you because it was not an actual point on the function. It should be 0, 3, not 0, 4. So to find the equation of a line, you're going to use point slope formula. And so you need to know a point on the line, which check, we do, that was given. And then we need to know the slope of the line. And that's where the calculus comes in. We're going to do the derivative to determine the slope. All right, the derivative of 3 is 0, plus the derivative of x squared is 2x, minus, oh, well, let me rewrite this. I'm going to rewrite my original function y, because I don't like fractions, and I don't need one here. I'm going to make this 2x plus 1 to the negative 1 power, and then I'm going to put that negative 1 in the front. So this is 3 plus x squared plus the natural log of 2x plus 1. Much easier to take the derivative of that. So now my derivative is 0 plus 2x plus 1 over 2x plus 1. I don't need a natural log of e because that's just 1. That was the base thing. And then multiply by the derivative of the inside 2. Okay, so my derivative is 2x plus 2 over 2x plus 1. So my slope is the derivative evaluated at the x-coordinate of the point given. Always evaluate the derivative to determine the slope. You always should plug in a number for x. That's 2 times 0 plus 2 over 2 times 0 plus 1. So that's 2. And now I can just fill into the equation. Y minus 3 equals 2x minus 0. Okay, well, that's 2x plus 3. The next question here is to determine where this function has horizontal tangent lines. Horizontal line means the slope is 0. Tangent line slopes are derivatives. So I'm going to find the derivative, set it equal to 0, solve for x. Okay, let's think about this as a 1/2 power. So the derivative of something to the 1/2 is 1/2 to the negative 1/2. Keep your insides the same. Multiply by it, the derivative of it at the end. So that would be times 3x squared minus 2. That needs a parenthesis. Okay, so to clean this up, my derivative has a numerator of 3x squared minus 2 and a denominator of 2 square root of x cubed minus 2x minus 4. I want to know when this derivative is equal to 0 because those are the places where the tangent line is horizontal. That would be when the numerator equals 0, because when the denominator equals 0, then you have a slope that this doesn't exist, so we don't want that. We want a slope that equals 0. So x squared equals 2/3. This has two solutions, plus and minus the square root of 2/3. It does say to find the points, but I'm just going to leave it at the x values. Okay, two more questions. These are asking you to find the second derivative. To find the second derivative, you first find the first derivative. So this is not a product. It is just the derivative of 3 to a number of an exponential function. So that's the same thing times the natural log of the base, since the base is not e, now times -2, because the inside, remember, of an exponential function is the exponent part where the x lives, and -2x has a derivative of -2. Okay, I'm going to rewrite this a little bit. This is -2 ln 3 to the -2x. Okay, this does not need the product rule, but there's definitely some products up here. So what is the exception in that this does not need the product rule? You can do the product rule. It's because this -2 has no x. This natural log of 3 has no x. No x means constant. X is the variable. It varies. Derivatives measure rates of change of variables. Rates of changes of constants are nothing because it's constant. The rate of change or the derivative is 0. And so this follows under the constant multiple rule. And the constant multiple rule, constant multiples hang out and you measure the rate of change of the variable that it's multiplied to. And they just stay in the front and stay multiplied. So what is this derivative of the derivative, or the second derivative? Well, -2 ln 3, those are constants. Those just stay there. Now times by the derivative of the non-constant part, which I'm highlighting in green right now, the derivative of 3 to the -2x. You just did that, right? That was the first derivative. The derivative of 3 to the -2x is the same thing, times the natural log of 3 times -2. So I used the natural log of 3 because that was the rule for the derivative of a base non-e. It stays the same, times the natural log of the base, times, if you need to, the chain rule, the derivative of the inside. And so when we clean up this second derivative, we get 4 times the natural log of 3 squared, which is not the natural log of 9 or anything like that, or 6, or it's natural log of 3 times natural log of 3 times 3 to the -2x. This is as simple as that goes. Okay, last question. Second derivative. This time we do have a quotient, and so we will use the quotient rule. And this is, I told you you need to simplify some things, and so you're going to have to simplify this in order to do our second derivative nicely. Oh, since this is a quotient rule, let me label our f's and g's. So f is the numerator, e to the 2x. Its derivative is 2e to the 2x. G is the denominator, x to the 1/2. Its derivative is 1/2 x to the -1/2. So to find the first derivative of our function f of x, that would be f prime g minus fg prime. All divided by g squared. Square root of x squared is x, or x to the 1/2 squared. I'm going to write that on the side here. You multiply exponents when they're raised to each other. Okay, so let's simplify this. What is common that will factor out? Well, an e to the 2x. Those are both in the numerator. So I'm going to factor out an e to the 2x. Also, I have an x. I'm going to factor out an x. I choose the smallest exponent to factor out. That would be a -1/2. Okay. I also want to factor out the 1/2. Why not? I know that 1/2 doesn't, well, 1/2 does go into 2. It goes into 2 4 times. So what do we have left? Well, 2 divided by 1/2 is 4. I took out the e to the 2x, and then x will be now to the 1 power because I had a 1/2 power. I factored out a negative 1/2 power. Remember, when you factor out, you divide. When you divide, exponents subtract. So this is a 1/2 minus a negative 1/2, or an x to the 2 halves and x to the 1. Minus, I took out the 1/2, I took out the e to the 2x, I took out the x to the negative 1/2, so that's just minus 1 is left, all divided by x. So the last step here, I'm going to say this is e to the 2x times 4x minus 1, and then down in the denominator I have this 2, but I'm going to put him down in the denominator where he lives. And then this x down here was to the 1, and then the numerator was to the 1/2. That will be a 3/2 in the denominator, because I can take this negative and I can make it positive by moving it to the bottom, and then you add the exponents once they're down there together. This is the nicest version of f prime, believe it or not. And in this version, and in all versions, you're going to have to use a product rule and a quotient rule. Wow. Okay. Let me do the numerator first. I'm going to label the numerator e to the 2f, and that's e to the 2x times 4x minus 1. It is a product, because see how you have an x in both parts. So I'm going to label the f e to the 2x and the g 4x minus 1. The f prime is 2e to the 2x. The g prime is 4. And so when I use the product rule here, the derivative of the numerator of the function is f prime g, not the g, plus fg prime. Okay, so that's the numerator. I took care of the numerator. I called him f. Now the denominator, g, what color should I use? Red. G is 2x to the 3/2. This is my g. And so what is g prime? 3x to the 1/2. And so now I'm going to use my quotient rule. So the second derivative of f, the derivative of the first derivative, where f is my numerator and g is my denominator, is, I'll color code it for you, f prime g minus fg prime over g squared. All right, so what is that? Okay, so this is 2e to the 2x, 4x minus 1, plus 4e to the 2x. That's the f prime. That was this in green here. Times g. G was much simpler. He was just 2x to the 3/2 minus f. F in itself is not a pretty guy. E to the 2x, 4x minus 1. Times g prime, who is just 3x to the 1/2. All divided by g squared. G was 3x to the 1/2. That'll be it. No, that was g prime. G was 2x to the 3/2. When I square that, that will give me 4x cubed. Okay, so again, this is my f prime here. This was my f. This is my g, and this is my g prime. I'm going to go ahead and simplify this. Okay, and then we'll be done. In this numerator, I have, well, in this green one, I have e to the 2x and 2. So let me fix this green one. Let me factor him. He would be 2e to the 2x, 4x minus 1 plus 2. So this was the original bracket. And so that's 2e to the 2x times 4x plus 1. So this is the f prime. I just factored it a little bit. Let me rewrite what I have. 2x to the 3 halves. So I'm not factoring out anything from the whole entire thing yet. I just fixed the f prime a little bit. Okay, now let's factor out a common factor. So a common factor between these two are e to the 2x. So I'm going to factor out an e to the 2x. Let me use blue. Now this is 4x plus 1, and that's 4x minus 1, so those do not factor out. Let me just get rid of that. All right, but then I do have an x, right? And I'll factor out the x with the lowest exponent, which would be 1/2. All right, got my 2x. All right, so who do I have left? In the first term, I have 2, 4x plus 1. I have another 2. Let me just make that 4. 2 times 2 is 4. 4x plus 1, and then the x will be now to the 2 halves, or just x, minus, I took out the e to the 2x, I have this 4x minus 1, and I have a 3. Almost done. 4x cubed. This is just what the answer on a multiple choice test would look like. Okay, so in the denominator, I'm going to move this x to the 1/2 down. And so this is x to the 3, which is 6 halves, minus 1/2 is x to the 5 halves. Still keep the 4 there. I have e to the 2x. And now inside this parenthesis, this term here is going to give me 16x squared plus 4x. I've just distributed. And this term here is 12x minus 3. I'm going to subtract that. So be careful to distribute the negative. This is 16x squared minus 8x plus 3 because I distributed that negative. This would be the answer on a multiple choice test. On a non-multiple choice test, which is your test tomorrow, you could leave it right here, okay? But on a multiple choice test, like maybe your final exam, then you would have to match it up to the right answer there. And that's all.